A very good afternoon to one and all present here. Welcome back for the third session of the day 4 of FDP on trends in MEMS and nanotechnology, sponsored by Atal Academy, New Delhi. We have with us our next eminent speaker, Dr. Jayaram, who will be delivering a talk on MEMS sensors. On behalf of Department of EC, I extend a very warm welcome to you, sir, for this FDP.
Thank you, sir. Thank you.
I now request Ms. Megha to introduce our next speaker, Dr. Jayaram.
Good afternoon to one and all. I, Megha R, on behalf of Department of Electronics and Communication Engineering, feel pleasure to introduce our resource person, Dr. Jayaram A. Dr. Jayaram is a faculty at Alvas Engineering and Technology. Sir has more than 20 years of hands-on experience in engineering and fabricating metallic or magnetic thin films by sputtering and spin coating. Sir has hands-on training in lithography and device fabrication facility, especially the MEMS facility at IIT Bombay. Sir has organized 4 international conferences as convener. Dr. Jairama was the editor of Sahyadri International Journal of Research and was a guest editor for Materials Today. Dr. Jairama has received an award for research publications from Vision Group of Science and Technology. Some of his research areas includes methanol fuel cells, hydrogen fuel cells, biosensors such as ammonia, hydrogen sulfide, methanol sensors, ethanol sensors, optical limiting materials, and piezoelectric MEMS cantilever vibration sensors. Sir has over 86 publications in SCL peer-reviewed journals and has filed 6 patent applications. We are honored to have you. Welcome you, sir. Over to you, sir.
Thank you. Thanks for introducing me. Good afternoon to everyone. First of all, I thank the organizing committee, especially the HOD, Professor D.V. Manjunath, for giving an opportunity to give this invite talk. We have done some cantilever work at IIT Bombay. One of our students worked in this particular area. I thank my colleague Professor Richard Pinto. Under his guidance, we worked under Indian Nano Users Program, and there we developed MEMS vibration sensors as well as energy harvesters. First, I will brief some of the basics. After that, I will come across our results. It is mainly MEMS energy harvesters, MEMS based energy harvesters, and MEMS based vibration sensors. And in detail, I will explain the fabrication technique and sensors, its types, fabrication techniques, MEMS manufacturing technology, this and all we will cover. We can discuss. MEMS, what are MEMS? It is a micro electromechanical systems. It's a technology that in its most general form can be defined as miniaturized mechanical and electromagnetic elements that are made using the techniques of microfabrication. The critical physical dimensions of MEMS, the dimensions of MEMS vary from 1 micrometer to several millimeters, few millimeters. Likewise, the types of MEMS devices can vary from simple structure having no moving elements to extremely complex electromechanical systems with multiple moving elements like car under the control of integrated microelectronics. So this is micro means it is smaller in size. Electromechanical systems. System is a integrated system like a mobile phone. It's a system. In brief, MEMS is a technique of combining electrical and mechanical components together on a chip to produce a system of miniature dimensions. It's the integration of millions of transistors on a single chip, which allows the microsystem to both sense and controls the environment. The components are integrated on a single chip using microfabrication technique. Where do you find MEMS? MEMS you can find in printers, high DPI inkjets. MEMS technology is used in the manufacture of inkjet print heads. This involves the formation of a tiny mechanical system on a substrate such as silicon or glass, which requires sophisticated micro-level microfabrication technology. For example, Konica Minolta has used this MEMS manufacturing technology for the high definition, high precision fabrication of nozzles and ink channels, which affect the characteristics of print head ejection. We can see MEMS technology in projectors, micromirrors from Texas Instruments. A digital micrometer means it is a device. It's an optical micro electrical mechanical system that contains an array of highly reflective aluminum micromirrors. These chips are often used for high-speed industrial, medical, and advanced display applications. Cell phones, noise microphones, used in most new cell phones. Today's smartphones sensors can include MEMS-based accelerometers, microphones, gyroscopes, temperature and humidity sensors, light sensors, proximity and touch sensors, magnetometers, barometric pressure sensors, and capacitive fingerprint sensors, all integrated to wireless sensor nodes. And these MEMS also mainly used in automobiles. MEMS sensors are indispensable in vehicles and electronic devices today. The first versions were used in motor vehicles as pressure sensors and accelerometers. Over time, the largest technology driver for MEMS changed from automotive applications to consumer electronics dominated by smartphones. MEMS sensors have become the heart of whole class of new devices like fitness trackers, smartwatches, virtual reality glasses, and smart sensor nodes for IoT. IoT means Internet of Things. So as I told, why MEMS? It is because it is smaller in size. A typical dimension is 1 nanometer to few millimeter. Say for example, human hair. This is about the dimension 50 micron is the thickness of the hair, and around 1000 micrometer sugar grain. Sugar grains is around 1 millimeter size, right? In packing, in the dimension, it's 1 millimeter. 10 micrometer is the size of RBC, red blood cells. MEMS are well known mainly because one is low cost. The most significant MEMS device product includes waveguides, optical switches, cross-connect multiplexers, filters, modulators, detectors. Their small size and low cost, low power consumption, mechanical durability, high accuracy, a high switching density, and low cost back processing of these MEMS based devices make them a perfect solution to the problems of the control and switching of optical signals in telephone networks. Most of the MEMS fabrication processes are done on silicon wafer. This is a silicon wafer made primarily on silicon wafer. MEMS flow sensors accurately detects minute airflow so much as a single flap of a butterfly wings. A gas flow sensor capable of measuring mass flow independent of temperature and pressure. The well-known company which supplies, you might be knowing, that is Omron. Omron BP measurement meters are well-known. MEMS air and gas flow sensors are highly resistant to dust. It has built-in dust segregation system. The sensor can be placed anywhere thanks to its dust resistant structure. Here, the favorable scaling for a lot of application, that is another one is electrostatics. Electrostatics plays a prominent role in micro and nanomechanics, while other forces such as thermoelectric forces, piezoelectric forces, and even magnetic forces are used in micro and nanomechanical systems, that is a MEMS and NEMS. Electrostatic forces are by far the most commonly employed. Electrostatic forces are used to move mechanical components in electrostatic systems and fluids in electrostatic fluidic systems. And this favorable scaling of a lot of applications includes magnetism. Magnetic MEMS present a new class of conventional MEMS devices with great potential for science and applications. Magnetic MEMS are based on electromagnetic inductions between magnetic materials and active coils or passive magnetic field sources like permanent magnets and many others. Briefly, the sensor, it is a device used to measure a physical quantity such as pressure, sense, temperature, and to convert it into electric signals of some kind, example, a voltage, or without modifying the environment. So, what and all MEMS can sense pressure, temperature, flow rate, radiation, chemicals, pathogens using these techniques, that is, using these sensors, two axis magnetic sensor, accelerometer, light intensity sensor, humidity sensor, pressure sensor. Speciality is they are all small in size. The advantages, MEMS have both advantages and disadvantages. The advantages are MEMS switches and actuators also can attain very high frequencies. They are smaller in size. MEMS devices require very low power consumptions. MEMS can be readily integrated with microelectronics to achieve an embedded mechatronic system. It improved reproducibility, high accuracy, sensitivity, and selectivity, cheaper due to mass production. MEMS sensors possess extremely high sensitivity. These are all advantages. Scaling effect at a microscopic level can be leveraged to achieve the design and dynamic mechanisms otherwise not possible at micro scales. And mainly easier to alter the part of a device as compared to its macro counterparts. Disadvantages also there. One is mainly it is expensive, very expensive during the research and in R&D stage. Any new MEMS designs or devices cost a lot of money because R&D structure in the R&D stage it requires more cost. Fabrication assembly unit costs can be very high and low quantities. Therefore, MEMS are not suitable for only unique applications unless cost is not an issue. And most of the MEMS devices are made of silicon. Polysilicon is a brittle material. Farm establishment require a huge investment. Prior knowledge is needed to integrate MEMS device. The design includes very complex procedures. And these are very expensive upfront setup cost for fabrication, clean rooms, and boundary facilities. And again, the testing equipment to characterize the quality and the performance can also be expensive. These are all different types of sensors, mainly classified into four categories: mechanical sensors, optical sensors, thermal sensors, chemical and biological sensors. In mechanical sensors, these are the process, means physical concepts or the material properties are used in a mechanical sensor. One is piezoresistivity and piezoelectricity. The type of mechanical sensors are strain gauges, accelerometers, pressure sensors, microphones, etc. Strain gauge means strain gauge measures how structures, both man-made and biological, react to an applied strain. These devices are common in the mechanical and civil engineering fields for monitoring structural health of bridges, detecting soil pressure changes near oil drilling platforms, and testing aircraft components. And these strain gauges can even be used to analyze bone structure in humans and animals. In the field of civil engineering and the in biomedical field, strain gauges are used to measure deformation sustained by various objects. Typically, foil gauges are used, but they have low sensitivity. And these are the two physical principles used in or the material properties. One is piezoresistivity and piezoelectricity, and both these kind of materials are used in mechanical sensors. Piezoresistivity means it is a it is an effect exhibited by various materials that exhibit a change in resistivity due to the applied pressure. Piezoresistivity means change in resistance due to applied pressure. In the same way, piezoelectricity means it is a change in electric charge when subjected to an applied mechanical force. It is a direct effect. In piezoelectricity, there are two types. One is direct, other one is indirect. Indirect means if you apply voltage, material vibrates, material changes its size. That is indirect. Direct means when you apply pressure, material generates voltage. That is piezoelectricity. Piezoresistivity means resistance changes due to the applied pressure. And these two properties you can observe, that is based on the crystal structure. Mainly the crystal structure should be non-centrosymmetric so that you can observe piezoelectricity or piezoresistivity. And capacitive techniques. The technique provides a precise way of sensing the movement of an object. This is, you might have heard about a parallel plate capacitor. In that, the the capacitance depends on the spacing. Essentially, the devices comprise a set of one or more fixed electrode and one or more moving electrodes. And this is optical technique. Optical sensing techniques primarily rely on modulating the properties of an optical frequency electromagnetic wave. Electromagnetic wave means there are variety of frequencies. In this case of optical sensors, measurand means measured quantity directly modulates the properties of the electromagnetic wave. This is in optical properties. In the case of microsensors, which use optical interfacing, the miniaturized sensor interact with the measurand. The microsensor then modulates a property of the optical signal in order to provide an indication of the measurand. Resonant techniques, the resonance means when the applied frequency match with the natural frequency, resonance frequency, that is a basic. The basic principle is applied frequency must match with the natural frequency so that resonance takes place. In the resonator, it's a mechanical structure designed to operate designed to vibrate at a particular resonant frequency. It can be fabricated from a range of single crystal materials with micron-sized dimensions using various micro-machining processes. The resonant frequencies of such micro resonators are extremely stable, enabling them to use as a time base. You can see this kind of resonant vibrating structures in fork tuning forks and in watches and in many resonant sensors. In mechanical sensors, actuation technique also used. We are focusing on mechanical sensors, and these optical sensors, thermal sensors are these are the types, but we are focusing mainly on piezoelectric materials. Okay, actuation technique means it is specifically a mechanical actuator is one that translates a signal from electrical domain into the mechanical domain. Okay. The typical applications, the main application, MEMS, well-known application is in accelerometers. Accelerometers can be used to measure vehicle accelerations. You might have seen simple pendulum. Simple pendulum in that when it oscillates at the extreme ends, velocity is zero, right? And in the mean position, velocity is maximum. Means based on the position, accelerometer can be used to measure vehicle acceleration. The principle is same as in the simple pendulum. Accelerometers can be used to measure vibration on cars, machines, buildings, process control systems, and safety installations. They can also be used to measure seismic activity, inclination, machine vibrations, dynamic distance, and speed. You might have seen in mobile phones, you can measure the distance while walking, right? That is by using accelerometers. Applications for accelerometer that measure gravity, wherein the accelerator is specifically configured for use of gravimetry. Others, such things are called gravimeters. Accelerometers generally used to measure the motion and vibration of a structure, thus it is exposed to dynamic loads. Dynamic loads originate from a variety of sources, which includes human activity. Means while walking, one can generate charge and we can store human activities like walking, running, dancing, skipping. Uh, Through that, one can generate energy. Working machines like inside a building or in the surrounding area. So these are dynamic loads. Dynamic loads also includes moving loads on bridges, vehicle movement on bridges. That's a dynamic load. That vehicle oscillations, impact loads, etc. And another other applications is magnetometers. Magnetometer means it is a device that measures magnetic field or magnetic dipole moment. Different types of magnetometers measure the direction, strength, or relative change of a magnetic field at a particular location. The best example is a compass. Is one such device, one that measures the direction of an ambient magnetic field. In this case, the Earth's magnetic field. Other magnetometers measure the magnetic dipole moment of a magnetic material, such as a ferromagnet. For example, by recording the effect of this magnetic dipole on induced current in a coil. And the another application of a MEMS, it is in microphones. Microphones, it is also called mic, or mic is a device, a transducer. What it does, that converts sound into an electrical signal. Microphones, it converts a sound into an electrical signal. Microphones are used in many applications such as telephones, hearing aids, public address systems for concert halls and public events, motion picture production, live and recorded audio engineering, sound recording. In these areas, mics are used, microphones are used. The other application is microfluidics. Microfluidics, best example is inkjet printhead. Inkjet printhead. In that, both the science which studies the behavior of fluids through microchannels and the technology of manufacturing micro miniature devices containing chambers and tunnels through which fluids flow are confined. The other application is RF MEMS, radio frequency micro electromechanical systems. Radio frequency micro electromechanical systems, in that it is actually a switches. These switches are the specific MEMS switches that are designed to operate at radio frequency to some millimeter wave frequency. MEMS switches usages some mechanical movement to achieve a closed or open circuit in the radio frequency transmission lines. And the applications also include a bridge to nanotechnology. Bridge to nanotechnology means it is bridging micro and nanoscale. Bridging micro and nanoscale. For example, OSAM. OSAM means oriented self-assembly on MEMS. This approach in which DNA is utilized to bridge MEMS and nanotechnology. The automotive MEMS sensors and actuators used to control various elements of the automobile, okay, like powertrain and chassis control, manifold air temperature. That's one of the example of automotive MEMS. Comfort and convenience, air temperature control, communications, wireless. And this is begin. First, it was recorded use of MEMS in automobiles. In MEMS inspired sensors based engine management was initiated in around 1979 to decrease a tailpipe emission. Okay, it is there in automobiles. Starting in 1979, the microprocessor based automotive engine control module was phased in to control the engine air to fuel ratio, fixed at the stoichiometric point. By doing this, the catalytic converter efficiently minimizes tailpipe emissions, bringing them into compliance with the federal regulations. Okay. Many different sensor technologies are introduced to solve this problem. MAP means manifold absolute pressure, and MAT, manifold air temperature sensors, were developed using MEMS. Silicon-based MEMS sensors became the device of choice due to low cost and high yield. These are different types of sensors, current and futures automotive sensors. You can see many sensors: oil quality sensors, coolant temperature sensor, vehicle speed sensor, steering rate sensor. A variety of sensors you can see in this. And fuel level sensors, fuel tank pressures, all the some of these sensors are there in ordinary cars also. Okay, in expensive cars, most of the sensors are existing. Who developed these? There are two groups. One is Delco Electronics Group, that is General Motors. They used piezoresistive sensing in the around mid 70s. Delco Electronics. And another company is Ford. developed two types of map. Map means manifold absolute pressure. The Delco version had a sensor die. It had a sensor die similar to the Honeywell sensor die of the time, and was packaged in a housing similar to the Fairchild ignition module. This product and versions of it are still manufactured by Delco and other aftermarket suppliers. Similar versions of this sensor were developed for all major car companies in the world, and its specification is the de facto industry standard. The Ford version was a silicon variable capacitance pressure sensor. It is still manufactured today by both Ford and Motorola company. However, it is not used by any other car manufacturer. It is more costly than the piezoresistive version. Delco uses piezoresistive sensing version. There are other thick film hybrid map sensors also serving this market. Our focus is on piezoelectric. This is about piezoresistive. Whatever you have discussed, piezoresistive means when you apply the pressure, resistance changes. That's a material property, piezoresistive sensors. So this is a diaphragm structure with the two embedded piezoresistors. Use the piezoresistive effect, apply stress, changes resistivity of materials. And capacitive sensors, as I told, it is best example is parallel plate capacitor. There are two parameters. One is gap spacing and the overlap area. This gap, that is the spacing between two electrodes represented by G, and area is represented by A. It is in meter square of the smallest of the two plates and inversely proportional to distance of separation. See, the capacitance, in the case of capacitance of a parallel plate capacitor, it is proportional to area A, and area A between the two plates and inversely proportional to the distance of separation. Okay. And advantages in this parallel capacitor, A is area and G is the spacing, and epsilon is permittivity of free space. It is a well-known value. It is in farads per meter, 8.854 in 10 to the power minus 12. These capacitive sensors act like a simple capacitor. A metal plate in the sensing phase of the sensor is electrically connected to the internal oscillator circuit, and the target to be sensed acts as a second plate of the capacitor. See, parallel plate capacitor means it has two plates, right? So one is fixed, other one is oscillating, right? Oscillating, that is accelerometer, oscillating. So based on this capacitor sensor works. The capacitive MEMS pressure sensors are one of the most widely used transducers of various MEMS pressure sensors, since they offer excellent noise performance, low power consumption. These are the advantages of capacitive sensor. One is low power consumption. Okay, and it also has a disadvantages, as the capacitance of a MEMS capacitor is usually MEMS capacitor. It is the capacitance is very small. That stray capacitances and parasitic capacitance are relatively large. Therefore, this is the main disadvantage. When you say the effect of it affects stray capacitance and parasitic capacitance. Parasitic capacitance means unwanted capacitance are relatively large. Therefore, special attention has to be paid to these effects in the design of sensing structure and circuitry. Okay. So parasitic capacitance and its disadvantages. Advantages covers it has requires low power and it is temperature independent, etc. It's about capacitive sensors, actuators. The main one of the MEMS actuator. It is traditionally only sensors were developed for automobiles. Actuator, it's a component of a machine that is responsible for moving and controlling a mechanism or system. For example, by opening a wall. In simple terms, it is a mover. An actuator requires a control signal and a source of energy. It requires a control signal and a source of energy. Actuators started to become popular as MEMS development cost decreased. In the engine control system, actuator regulates idle speed, control air flaps or torque and power optimization, and meter fuel for optimum combustion. In convenience systems, they are used to lock and unlock car doors. For example, for the remote control of fuel filler flaps, boot lids, engine bonnets, and storage compartments. Popular actuators include microphones and fuel injection nozzles. Microphones and fuel injection nozzles. This is about micros MEMS sensor fabrication. MEMS sensor fabrication. Uh, there are few steps for the fabrication. Important steps one must know. One after undergoing MEMS FDP, one must know at least few fabrication techniques. The first step is wafer production. All of you know, usually silicon wafers are used in the fabrication. So I'll brief about how we get a silicon wafer. That is the first step. First step of wafer production. Step is wafer production. The wafer is a round slice of semiconductor materials such as silicon. Silicon is preferred due to its characteristics. It is more suitable for manufacturing ICs, integrated circuits. It is the base or substrate for entire chip. First, purified polycrystalline is created from the sand. Sand is heated to produce molten liquid. It has to be heated very high temperature because melting point is high for sand. A small piece of solid silicon is dipped on the molten liquid. Then the solid silicon is slowly pulled from the melt. For the growth of silicon ingots, they use melt technique. The liquid cools to form single crystal ingot. This is one of the crystal growth technique. Crystal growth techniques, many crystal growth techniques you might be knowing. Well known is solution growth technique. And this is a melt technique. Through melt technique, they grow silicon ingots. A thin round wafer of silicon is cut using wafer slicer. Wafer slicer is a precise cutting machine and each 0.01 to 0.025 inches. When wafer is sliced, the surface will be damaged. And this surface will be smoothening by polishing. After polishing the wafer, it must thoroughly clean and dry. The wafers are cleaned using high purity, low particle chemicals. The silicon wafers are exposed to ultra pure oxygen. there is a growth that is called epitaxial growth. That means the growing of a single silicon crystal upon original silicon substrate. A uniform layer of silicon dioxide is formed on the surface Si and SiO2. It's a very good combination. Usually, when you slice silicon, SiO2 will be automatically coated on the surface of masking. That is one of the important step to protect some area of wafer when working on another area, a process called photolithography. I'll show you the picture here. Photolithography later is used. The process of photolithography includes masking with the photographic mask and photo etching. Here, they use a photoresist film is applied on the wafer. The wafer is aligned to a mask using photo aligner, MJV mask aligner. That's a well-known aligner. Then it is exposed to ultraviolet light through mask. There also one has to optimize the intensity. Before that, the wafer must be aligned with the mask. Generally, there are automatic tools for alignment purpose. And the third step is etching. Etching removes material selectively from the surface of a wafer to create patterns. Etching, the main purpose of etching to create patterns. If you want a cantilever pattern, you have to make a mask of cantilever, and the parts of materials are protected by this etching mask. There are two etching techniques. One is wet chemical etching and dry chemical etching. Dry physical etching can be used to remove the unmasked material. To perform etching in all directions at the same time, isotropic etching will be used. Isotropic means velocity of light is same in all directions. Isotropic media, isotropic. Isotropic etching means in all the direction it will etch uniformly. Isotropic etchings. Anisotropic etching is faster in one direction. For example, KOH. KOH is used in as it's a anisotropic etching. Wet etching is isotropic, but etching time control is difficult. Wet etching uses liquid solvents for removing materials, but it is not suited to transfer pattern with submicron feature size, and it doesn't damage the material. Dry etching, whereas dry etching it uses gases to remove materials. It is strongly anisotropic, but it is less selective. It etches everything, less selective. It is suited to transfer patterns having small size. The remaining photoresist is finally removed using developer, that is additional chemicals or plasma. Then the wafers is inspected to make sure that the image is transferred from mask to the top layer of wafers. Step 4, that is for doping. That is doping. Might have P-type and N-type semiconductors. Those are doped semiconductors. In the case of P-type semiconductor, boron is doped, and in N-type phosphorus. So that the property of the material changes, conductivity changes, right? Diffusion is defined. So this doping is mainly to alter the electrical character of a silicon. Atom with one less electron than silicon, such as boron, and atom with one electron greater than silicon, such as phosphorus. One electron greater, one electron lesser. One electron lesser is boron, one electron greater is phosphorus, are introduced in the area. So for the development of a P-type silicon, boron is diffused. Whereas for the N-type, phosphorus is induced to reflect their conducting characteristics. Diffusion means it is defined as the movement of impurity atoms in semiconductor material at high temperature. Atomic diffusion is a well-known method to make p-type or n-type semiconductor. In this method, p and n regions are created by adding dopants into the wafer. The wafers are placed in an oven which is made of quartz and it is surrounded with heating elements. Then the wafers are heated at a temperature of about 1500 to 2200 Fahrenheit. The inert gas carries the dopant chemical. The dopant and gas is passed through wafers, and finally the dopant will get deposited on the wafer. This method can only be used for large areas. For smaller areas, it will be difficult and it may not be accurate. Another doping technique is ion implantation. Diffusion is one technique, atomic diffusion is one technique, ion implantation is another technique. This is also a method. It is used for adding dopants. In this method, dopant gas like phosphine or boron trichloride will be ionized first. Then it provides a beam of high energy dopant ions to the specified regions of a wafer. It will penetrate the wafer. The depth of the penetration depends on energy of the beam. By altering the beam energy, it is possible to control depth of penetration of dopants into the wafer. The beam current and time of exposure, it is used to control the amount of dopant. Beam current and time of exposure. Beam current and time of exposure, through that we can control the amount of dopant. This method is slower than the other method. Other method is atomic diffusion. Compared to atomic diffusion method, ion implantation method is much slower. It doesn't require masking, and this process is very precise. First, it points the wafer that where it is needed and shoot the dopants to the place where it is required. The fifth step. It is metallization. Metallization generally it is used to make contacts. It is used to create contact with the silicon and to make interconnections on chip. And thin layer of aluminum. Aluminum is a cheaper material. It is deposited over the whole wafer. And aluminum is selected because it is a good conductor, has good mechanical bond with the silicon, forms low resistance contact, and it can be applied and patterned with the single deposition and etching process. And through this process, process 2, 3, 4, using process steps 2, 3, 4, we can make successive layers, multiple layers. The process such as masking, etching, doping will be repeated for each successive layers until all integrated chips are completed. Between the components, silicon dioxide is used as insulators. SiO2 is a insulator. This process is called chemical vapor, CVD technique, chemical vapor deposition. To make the contact pads, aluminum is deposited. The fabrication includes more than 3 layers separated by dielectric layers. For electrical and physical isolation, a layer of solid dielectric is surrounded in each component, which provides isolation. So it is possible to fabricate transistors like PNP transistor, NPN transistor in the same silicon substrate. And to avoid damage and contamination of circuit, final dielectric layer that is called passivation. passivation. Okay, it is deposited. After that, otherwise the device will damage, oxidation take place. So to avoid that, they do this passivation. Passivation means to avoid damage and contamination of a circuit, a dielectric layer is deposited. It's called passivation. After that, individual integrated circuits will be tested for electrical function and to check the functionality of each chip on wafer. And those chips are not passed in the text, it will be rejected. Okay, so if the chip is not functional, it will be rejected. The final step also includes assembly and packaging. Assembly and packaging. Each of wafer contains hundreds of chips, and these chips are separated and packaged by a method called scribing and cleaving. Scribing and cleaving are the two methods used to separate chips. The wafer is similar to a piece of glass. A diamond socket the wafer into single chips. The diamond tipped tool is used usually to cut the lines through the rectangular grid which separates the individual chips. The chips that are failed in electrical tests are discarded. Before packaging, remaining chips are observed under microscopes, and a good chip is then mounted onto a package. A thin wire is connected using ultrasonic bonding. It is then encapsulated for protection. Before delivered to customer, the chip is tested again. There are three configurations available for packaging. They are metal can package, ceramic flat package, and dual inline package. These are the three types of packagings. Specifically for military applications, the chip is assembled in ceramic packages. The complete integrated circuits are sealed in anti-static plastic bags. And in addition, this MEMS specific fabrication techniques, deep reactive ion etching, that is one of the etching fabrication technique, and silicon on insulator. Okay, these are the steps of fabrications. Say this is silicon ingot. Step 1, silicon wafer, polished wafer, 1 and 2. 1 and 2, that is, first one is ingot, and ingots are sliced, and we get silicon wafers. Those wafers are polished, and this is the magnified section of SiO2. This is lithography. Light is exposed on wafer using it is passes through a mask. So pattern being repeated onto wafer, that is called photolithography. And this is the close-up of a chip pattern with photoresistor. There are two. One is positive photoresist, other one is negative photoresist. Okay, and the fifth one is photoresist silicon dioxide wafer. Silicon photoresist silicon dioxide wafer etch silicon etch chip section. Okay, this one. And the sixth one is additional layers. If you want, it is deposited here, and additional layers such as polysilicon, doped silicon wafers, and conductive metal. This is metal. Step 8 here, stage 8. That is, they made contacts using conductive metal. Well-known material is around 140 nanometer, and after that gold will be deposited, because to increase the adhesion they add chrome, doped silicon oxide, and these are the chips. This is the schematic of a step for IC fabrication. Okay, so MEMS fabrication use basic IC fabrication, DRI and SOI. MEMS fabrication, specific fabrication includes deep, this is called deep reactive ion etching and silicon on insulator technique. Deep reactive ion etching means it is a highly anisotropic etch process used to create a deep penetration, steep sided holes and trenches in wafer substrate, typically with the high aspect ratios. In DRI, the substrate is placed inside a reactor and several gases are introduced. A plasma is stuck into the gas mixture, which breaks the gas molecules into ions. The ions accelerated towards and react with the surface of the material being etched, forming another gaseous element. This is known as the chemical part of the reactive ion etching. There is also a physical part. If ions have enough energy, they can knock atoms out of the material to be etched without chemical reaction. In semiconductor manufacturing, silicon on insulator technology, SOI, silicon on insulator technology, it is a fabrication of a silicon semiconductor devices in a layered silicon insulator, silicon substrate, silicon insulator, silicon substrate. To reduce this, the main purpose is to reduce parasitic capacitance. Parasitic capacitance means unwanted capacitance within the device, thereby improving the performance. If there are parasitic capacitance, it reduces the performance of the device. So to avoid that, they use SOI fabrication technique. SOI. Parasitic capacitance means it is a stray capacitance. It is an unavoidable and usually unwanted capacitance that exists between the parts of an electronic component or circuit simply because of their proximity to each other. The general MEMS packaging, as I explained, the most important and expensive part of a MEMS sensor actuator, around 45% of the cost of designing of MEMS device is spent on packaging. Oftentimes, packaging constraints will prevent a design from being produced. Package can greatly change the response of a device, sensitivity, dynamic range, etc., all affected by package. So there are two. Am I audible?
Yes, sir. Audible, sir.
Audible, no? Okay. Mainly there are two type of manufacturing processes. One is batch processing, bulk micromachining, and surface micromachining. These are the manufacturing processes. One is a serial focused ion milling, batch processing, and continuous. This is Dr. Blade technique, manufacturing coating technique, serial focused ion milling, batch example, bulk silicon micromachining, manufacturing techniques. Okay. MEMS manufacturing technology, here bulk micromachining, and in this there are two categories, as I told, wet etching and dry etching, and surface micromachining. This is deep micromachining, bulk micromachining. This is on the surface, fusion bonding, and this is a third manufacturing technique, high aspect ratio micromachining, LIGA. LIGA is a French word. So in brief, bulk micromachining means this technique involves the selective removal of the substrate material in order to realize miniaturized mechanical components. So here etched grooves, one is this is A, B, C. A is anisotropic etchant. B curved edge. This shape is curved, that is isotropic etchant. And here this is reactive etching, reactive ion etching. A widely used bulk micromachining technique in MEMS is a chemical wet etching technique, which involves immersion of a substrate into a solution of a reactive chemical that will etch exposed regions of the substrate at very high rates. A bulk micromachining means it is a process that produces structures inside the substrate by selective etching. Surface micromachining also has a etching process, but it is a process that creates structures on top of the substrate by film deposition and selective etching. I will show you the surface micromachining structures and bulk micromachining structures. I will spend some more time on bulk micromachining fabrication technique. After that, we will explain our results, how we fabricated, which are the steps we use for the fabrication of cantilevers, mainly beam cantilevers and cantilevers for the purpose of energy harvesting as well as for vibration sensors. Okay. This is the classification of bulk silicon etching. Bulk micromachining, it's a process that produces structures inside the substrate by selective etching. Two techniques, as I told, wet etching and dry etching. Okay. In wet etching, isotropic etchants are different, anisotropic etchants are different. Wet etching, isotropic etchants and anisotropic acidic. In isotropic etchants, acidic etchants are used, and anisotropic etchants, alkaline etchants are used. In dry etching, isotropic, this is xenon fluoride and bromine fluoride, and fluorine-based plasmas are used in anisotropic dry etching techniques. It is process dependent. We have to optimize. Here also in wet etching also we need to optimize. These are the etching of bulk micromachining, isotropic or anisotropic. See, this is I got some textbook. Wet etching of substrates. This substrate, usually silicon is a substrate, and this is the photoresistive material. Okay, and in between it is etched protective resist. Protective resistor. The black region is a protective resist and it's etchant. Okay, and here etchant substrate, etch substrate. This black region is protected because it is coated with the photo protective resist, right? So this is the etched substrate. In figure 9.2, the three principal planes in silicon crystals. One need to understand. One, if you are fabricating any device, you must know the planes of silicon wafers. Silicon, it is a cubic crystal. In this 100 plane, 110 plane. So you can make out the planes, and the third one is 111 plane. And isotropic, you can see the difference of isotropic etchants, etching shapes and design dimensions or shapes, and anisotropic etching of silicon substrate. So this is one of 100 plane of silicon wafer. This is unetched wafer. See this figure here, selectivity ratio of etchants in two silicon substrates. Okay, silicon dioxide, anisotropic etchant is KOH. Selectivity ratio is 10 cube. TMAH, EDP. These are different etchants. In this, selectivity ratios are different. Typical etching rates of silicon and silicon components in this, depending upon the type of phase, 100 phase, KOH, etch rate is different. If you use silicon 100 phase, if you use EDP as etchant, then etch rate is different, 0.75 micrometer per minute. And in silicon dioxide, SiO2, KOH is 40 to 80 nanometer per that is the H rate. Okay, so it has a different H, and mean main information is 100 orientation. Here in 100 orientation, wafer etched in 100, this angle is 54.74. Okay, and the main information is you must know the planes of silicon wafers before etching, and the selection of etchant is very important to optimize the etch rate. Etching features includes etch rate, that is rate of removal of a material in a film, per film. And it varies with the concentration, agitation, and temperature of etchant, porosity, and density of etched films. The selectivity, reactive etch rate of mask, film, and substrate. Etch selectivity, that's another parameter, and etch geometry. This is another parameter. Etch geometry. Geometry is most important while fabricating the device. So etch geometry. See the diagram in that the pink region U, that is a mask undercut. That is called mask undercut. In capital R means it's etching depth. So he can look, you can make out the symbol S. S means slope of lateral walls, and B is a bow of floor. So these are the parameters usually we consider while fabricating the devices while etching. This is bulk silicon etching. These are some of the examples. This is not our result. This is dry etching. Release etch by RI, rapid ion etching, and recess etch by rapid ion etching. You can make out the structure. It is very precise structure, clear structure. This is observed through the FSM. Deep cavity by wet anisotropic etching. And this is another example of a wet silicon etching this one. Here they use HNA. HNA is the combination of hydrofluoric acid, nitric acid, and acetic acid. Okay. See, look here. This is isotropic etching. Isotropic etching. See, this is the same images after etching. And here the masking layer is SiO2. SiO2 is used as a masking layer, and these are the images. This is silicon wafer. In anisotropic etching, they use KOH as the etchant. Here they use HNA as the etchant. Here they use KOH as etchant. See the shape, anisotropic, the shape. For this kind of structure, they use KOH. This is structure of single crystal silicon. As I told, different phases, 100 phase, 111 phase. One must have the idea or little knowledge about the crystal structure of silicon. This is face-centered cubic crystal. The structure, it is looked like a diamond structure with two atoms associated with each lattice point of the unit cell. Lattice point, unit cell, the sorts of those are all are the crystallographic terminologies. One atom is located in position with the XYZ coordinates. So these are the coordinates. Lattice constant for silicon, that is 5.43 angstrom. These are all about Miller indices, different planes. One plane, as I told, one plane, 100 planes. That naming is done based on Miller indices. It is a notation system in crystallographic for planes and direction in crystal lattices. A lattice plane is determined by three integers. One is H, K, and L, written as HKL. The indices are reduced to the smallest possible integer. That's a basic concept of finding Miller in the naming the planes. This is 111 plane. This is plane 221. And this is determining Miller indices. There is a specific procedure for the determination of a place by using Miller indices. These are all the basics. And these are the crystallographic planes and directions. See, you can see the shaded regions. This is 001 plane and 100 plane, and these are 1 bar 1 planes, different planes. This you might have studied in graduation courses. This is single crystal silicon wafer. Okay, silicon wafer. So this is primary flat, and this is secondary flat. While cutting silicon wafer, you must put pressure on at the middle of the flat region. Middle of the, you just, if you press, if you, it will cut horizontal. If you press here, it will cut vertical like that. Primary and secondary flats indicate the dopant type and surface orientation. Wafer diameter in current fab standards from 100 to 300 millimeter. This is the wafer size. Wafer thickness usually around 250 micrometer to 600 micrometer. And surface orientations, the different wafers cost, the cost is different for different wafers. 100 for generally they use for MOS, metal oxide semiconductor, and MEMS. And 110, this is also MEMS. For bipolar transistors, they use 111 plane silicon wafers. Standard 100 wafers, the position, see these are different wafers. This is primary flat in P-type 111 silicon wafer. This is N-type 111 wafer. Here you can observe the secondary flat. Okay, in P100 secondary flat is there, and N100. So these are the secondary flats and primary flat. The primary flat on 100 and 110 wafers is along the 110 direction. Orientation of a flats, orientation of a flats for 100 wafers. Wafers used in multi-MEMS are P-type. It's around 150 millimeter. Wafers used in multi-MEMS. They use P-type of 150 millimeter silicon wafers. 100 plus or minus 0.5 degree surface, and this is these wafers are primarily flat. This is the flat, and this is the silicon wafer, and this is the crystallographic structure, and this plane is 100, and this plane is 111. See, you can make out 110 plane in the cubic structure. 110 plane, that is like this. Okay, and this is 110 plane, and this is 100 plane, and 110 directions. This is the P-type 150 silicon wafer. You can make out the direction, which are the direction. You have to draw a schematic cubic, and you can make out this direction. This is 110 direction, then this is 100 direction. In isotropic wet etching of silicon, see the first diagram. This is with steering. Both are isotropic, with steering and without steering. Okay, you can see the difference. Isotropic wet etching of silicon. All crystallographic directions are etched at the same rate. Features are etchants are usually acids, and the etching temperature generally it is 20 degrees Celsius to 50 degrees Celsius. As the temperature increases, etching rate also increases. That is the general concept. Reaction is a diffusion limited, and very high rate etch rate is that is up to 50 micrometer per minute. That is the etch rate in isotropic wet etching of silicon, and there will be significant mask undercutting. Undercutting, you might have observed. This is undercutting. Masking is very difficult. Gold, chrome gold. As I told, chrome is used for adhesion. Gold is the contact. Is used for contact. Or low pressure chemical vapor deposition. Silicon nitride is good. Okay. Silicon oxide may also be used for shallow etching. This is about masking. Isotropic etching of silicon etchants. This is a table which gives the information about different etchants. This is the combination of HNA. HNA means hydrofluoric acid, HNO3, and acetic acid. Okay. So here typical composition they have taken. So the etch rate is 0.7 to 3 micrometer per minute. So see this, this is etched at a 22, all these are etched at a 22 degrees Celsius, and 10 ml composition, 30 ml composition, 8 ml composition. The range is 0.7 to 3 micrometer per minute. Whereas in this same this about the composition is different. H rate is 40. Same composition, but the composition is here HF 25 ml, HNO3 50 ml. This is acetic acid 25 ml. That means 4 is to 2 is to no 1 is to 2 is to 1. 1 is to 2 is to 1, right? This is 1 is to 3 is to 8, or you can find the ratio. Here HF 9 75 30 ml. This combination here, see, in one of the combination you can observe highest H rate, that is 40 micrometer per minute. So optimization of etchant, it is more important. Optimization. One of our student is working on glass etching. She's optimizing. So now still the optimization of etching of glass is going on at a Tata Institute of Fundamental Research. And see, this is the reaction, oxidation and oxide removal. This is SiO2 4. This is oxidation, and this is oxide removal. This is the mechanism of isotropic etching of silicons using different combination of etchants, HNA etchants. Silicon etching with the HNA, this is 23% hydrofluoric acid. This is 69 HNO3 and acetic acid. And HNO3 oxidizes the silicon. HNO3, the combination here in this table, the purpose of adding HNO3, what is the role of HF, and what is the role of acetic acid? This is mentioned here. HNO3 is used to oxidize the silicon. Okay, oxidization increases if you add more HNO3. Oxidization increases if you add more HF, whereas HF, it removes oxide. So one oxides, other one is removes oxide, and here HF, high HNO3 is to HF ratio, H limited by oxide removal. The H is limited by oxide removal. Low HNO3 to HF ratio, H limited by oxide formation. So here, if you change the ratio, the etching rate will become different. Dilute with water or acetic acid is preferred because it prevents HNO3 dissociation. Okay. So this is the ISO etch curve. This I collected from Robbins, one of the publications, Robbins et al. This is about isotropic etching of glass. Single or double side etching of glass wafers is achieved by either by using hydrofluoric water solution or combination of hydrofluoric acid, nitric acid, and acetic acid, HNA. Typical etch rate of a borosilicate glass in HNA is 1.9 micrometer per minute. So the applications are etching cavities and through holes, and etching gas, etching something. So look here, this is undercut and through hole, and this is the mask and this cavity, and this is the glass slide. Anisotropic wet etching of silicon. So look here, this diagram I showed. This here the angle in 111 plane, the angle anisotropic at 54.74, and you use this technique while fabrication of beams and cantilever in our experiment under INFP. One of the student, as I told in the beginning, Rashmi, she has worked in the INFP project and realized the cantilevers and beams. Anisotropic wet etching, crystallographic directions are etched at different rates. Features etchants are usually alkaline etchants. Etch temperature is 85 to 115 degrees Celsius. There it was around up to 50 degrees Celsius. Here it is high temperature because it's anisotropic wet etching. Reaction is rate limited. Low etch rate means 1 micrometer per minute. Small mask undercutting. Masking is very difficult. Low pressure chemical wave. So this is about anisotropic wet etching method. Etching setup. This is the etching setup. They use here. This is the condenser, and the nitrogen gas is passed here, and this is heating the wire, and the folder looks like this. See, this is silicon holding wafers holder. This is wafer holder. Wafers are mounted vertically in this. Wafers are mounted vertically. This thermometer is used to measure temperature. Okay, this is the laboratory setup for a wet chemical etching of silicon, and the principles for industrial manufacturing equipment are also the same. And again, as explained in the previous table, this is about anisotropic etching of silicon. Here the etchants are ethylene diamine, pyrocathocol, and water. The compositions at 750 ml, 120 gram, and 100 ml. We use this composition. H rate is 35 for 100, and for 1 plane 1 is 35 is to 1. So H ratio for 100 by 111. Okay. Here H rate is point. This is H ratio. H ratio 100 for etching rate is 35, or 111 etching rate is 1. H rate here it is H rate. The etchant H rate is 0.75 micrometer per minute. Masking film is this one. Okay, these are the masking film. So this is another combination 750, 120, 240 at 115 degrees Celsius. So this is 1.25 H rate micrometer per minute. So the H rate and H ratio are purely depending upon the composition of the etchants, diluents. Okay. So here this is TMAH. This etches smoothly. The surface etched by TMAH is always smooth. If you want to have rough surfaces, say for example, for the fabrication of transistors like MOSFET, metal oxide semiconductor field effect transistor MOSFETs, we need a smooth surface. That time you can use TMAH as the etchant. For the fabrication of this one, sensors, gas sensors, you need rough surface. That time you can use KOH as the etchant. Okay. Chemistry of anisotropic etching phases, transport of reactants to the silicon substrate, surface, and surface reaction, transport of reaction products away from the surface. This is the etching phase. These are the etching phases. Transport of reactants to the silicon surface, surface reaction, and transport of reaction products away from the surface. For that, stirrer is required. Continuously, it has to stir, right? Key etch ingredients are: one is oxidizers, oxide etchants, diluents, and transport media. Okay. So oxide etchants, that is depending upon the composition of HF, HNO3 and acetic acid. Okay, oxide. So this is the overall chemistry of anisotropic etching. Anisotropic etching of 100 silicon. See, these are the different phases. The cavity defined by 111 walls, 111 plane. This is 111 plane. So it etches in the direction. Okay. So this is 110 direction. So 100 plane. Here, this shape is called a truncated pyramidal cavity. Okay. 100 is this is a floor. This here etch rate is very high. It's called fast etching plane. Whereas this 111 plane, it is called a slow etching planes. This is a slow etching plane, 111 planes. And this is 111 plane. In this is V groove cavity. V groove cavity. This is oxide and V substrate. See the shape of H surface looks like. In this shape is it looks like a V shape, right? Here this is like a pyramidal cavity. Pyramidal cavity. Both these directions are reduced. This forms a pyramidal cavity. Final shape of cavity depends upon all this depends upon mask geometry, etching time, and etching rate. Shape of cavity, this is a truncated pyramidal cavity, this is V groove cavity, and this is pyramidal cavity. This is anisotropic etching of 100 plane of silicon. This is 100 plane. Here etch rate is maximum, and other planes etch rate is less. Cavity geometry for 100 silicon. See, this is 111 plane. This is 100. So the relation is to calculate exact amount of depth and this WB and W naught. You can adjust in such a way that by using this formula, this angle is a 54.7 degree, and this is standard for silicon anisotropy etched cavity in 100 silicon. The square masking film opening oriented parallel to the 100. So this standard, you have standard formula one has to use to etch silicon in a particular shape. WB is equal to, see, this is called a trapezoidal shape. So this type of trapezoidal shapes we have done, that is for a fuel flow. I think my colleague Professor Richard Pinto, he might have explained about hydrogen fuel cells or direct methanol fuel cells. There we etched in a trapezoidal shape because the flow rate was maximum in a trapezoidal shape. This shape we designed based on this formula, that is WB is equal to, WB means this is width, and W naught, that is this width, is minus 2L. L is the depth into cot 54.7. Okay, this is about mask undercutting. You see the diagram A. It is a pyramidal pit bounded by 111 planes. See, this is 100 direction. Here, this is 111 plane. 111 plane. This is 100 plane. Okay. See the B diagram B. It's a type of pit expected from slow undercutting of convex mirrors. So all depends upon the type of device you want to fabricate. See the diagram C, it's a type of pit expected from fast undercutting of convex corners. In D, convex, this is somewhat trapezoidal shape, right? D, further etching of C produces a cantilever beam. So this is a cantilever beam. Beam means it is supported by two ends in vertical direction. It's supported by two ends. Okay, towards you, it is supported by two ends. And E, it illustrates the general rule for undercutting, assuming a sufficiently long etching time. This is about mask undercutting and anisotropic etching of 110 silicon. Here, cavity is defined by 111 walls, flow etching planes 110. So this, as I explained, 11100 in this etch rate is maximum. So this is the mask. If you use different mask, you can get different shapes. And final shape of cavity depends upon mask geometry, etching time, cavity shape depends, maybe rhombic prisms, hexahedric prisms. So this is the cavity geometry for 110 silicon. This is vertical 111. This is slanted 111, vertical 111. So this is the geometry, and this is the top view. Methods of selective etching depends upon time of etching methods. It is to calculate the needed etching time on the basis of the etching rate, and chemical selective etching techniques. And here the etching stops when a chemically resistive layer is reached. Electrochemical selective techniques. This is about time stopped etching. Examples of etching stopped at an arbitrary depth. This is about etching stopped by 111 walls. Okay. Undercutting of convex corners. This also again depending upon the mask. And this is about compensation for convex corners. And this is about corner compensation structures, different structures. And these are the different designs with the undercut corners. And this is from a MEMS technology seminar. Okay. Designing with the undercut corners, you can make different shapes. This is a cantilever structure. And these are all bulk micro-machined silicon mask for cylindrical micromotion sensors. And this is a bulk micro-machined series connected photovoltaic converter battery. Okay, these are all FSM images. And this is series connected photovoltaic converter battery. Okay. And bulk micro-machined series connected photovoltaic converter battery. And see, in this micro thermal chemical power, in this is ant is in this is in the face of ant, a crown placed on ant's head. The crown was fabricated by a huge and highly precise conventional computer-controlled milling machine. We can produce such micro products of an individual basis, but the production cost is high and the cost-benefit ratio very low. And this is a criteria for Nippon Denso. The other one is in the manufacturing surface micromachining. Here you can see the diagram E. This is the final structure, final device. So initially there is a sacrificial layer is coated. Sacrificial layer can be a polyvinyl alcohol or some this one photoresistor. That may be a sacrificial layer. So sacrificial layer, and this is exposed, and this part is removed by etching, and again it is coated by polysilicon. This is polysilicon structure, and here this is etched further, and here it is developed so that the lower coating, that is sacrificial layer, is removed. That is done by patterning of a desired structure. This patterning, and E is the stripping of the spacer layer, is also final structure. So A is spacer layer deposition, B is patterning of the spacer layer, and C is deposition of the microstructure layer, and D patterning of desired structure. Stripping of the spacer layer results final structure. This is about silicon micromachining, high aspect ratio. Applications and medical devices, biocavity sensors in small pills and sight of a blind MEMS-based array that may be inserted in the retina of a blind person to provide partial sight. Applications in marine science, there are many: oil exploration and related applications, global weather prediction, monitor water quality for. Okay, so these are the some of the military operation also use. And these are the applications in marine military operations: detonating the torpedo at the right time, hitting the target in a crowded environment, prevent any premature explosion. This MEMS technology is used in defense also. Okay, and so this is about our work. I will briefly explain this since the time is short. Our work is mainly on energy harvesters uh, and vibration sensors in both the applications. The fabrication technique is same, but the applications are different. One is used for energy harvesting application, other one is for, we fabricated both beams and cantilever structures of a material, piezoelectric material, that is PVDF, TRFE, polyvinyl PVDF, TRFE. This is one of the expensive material. Each 100-gram sample costs around 1 lakh rupees. Initially, a brief about the energy harvesting harvesters, available alternative energy sources, and common energy harvesting systems, challenges from different sources of energy and energy storage. Finally, I will explain our results. So these are all photovoltaic solar cells. Okay, and implanted medical devices. This is wireless weather stations. Solar is the source of energy. Mechanical, this wind energy can be generated through wind, and this is through thermal power. This is through electro. These are the sources of energy. Energy storage. This is traditional rechargeable batteries. Then this is another energy storage system. This is capacitor, and this is supercapacitor. And challenges from different sources are light, vibrations, and thermal. These are the three sources of energy: light, vibration, and thermal. Challenges are we need high power output. Power output in the sense it has to generate more energy, more power. In these vibrations, we focus on vibrations piezoelectric. Here, power estimated power production is at 200 microwatts per centimeter cube. 200 microwatts per centimeter cube or centimeter square. Okay. This is about energy harvesting. Our main aim is to extract energy from human body. Human body, as you know, human. So look here. This is about piezo and piezoelectric effect. This piezoelectric effect means when you apply pressure, it generates voltage, and these are all the basics. This is about inverse piezoelectric effect. When you apply voltage, it vibrates, and this is inverse piezoelectric effect. And this is the basic mechanism, okay, of piezoelectric effect. And this is the origin of piezoelectric effect. Barium titanate. It's one of the crystal should be non-centrosymmetric. That is the message. Crystal should be non-centrosymmetric to generate voltage. These are the fundamentals of piezoelectric materials, and this is about crystal structure and dipole moments. polarizing piezoelectric materials. So these are all some of the piezoelectric coefficients in D and G for selected material. D means it is a coefficient when you apply 1 Newton of force, it generates charge. That is D coefficient, picocoulomb per Newton. This is D coefficient means picocoulomb means it is charge generated per unit force. This is voltage generated by unit force. Okay. So in this, Fizz T is a well-known material, but it is brittle, 268 to 480. And for well-known material is Fizz T, but it's ceramic and it is not flexible. Flexible. In this, none of the materials are flexible. We need flexible piezoelectric material for body energy harvesting. So our aim was to extract energy from the body. The body vibrates in the frequency range of uh, 50 to 100 hertz. Body vibration, body surface vibrates in the range of 50 hertz to 100 hertz. 50 hertz means in the case of Parkinson's patient, they vibrate around 10 hertz to body vibration, maybe around 10, 1 to 20 hertz range. Otherwise, if the normal person vibrates 50 hertz to 100 hertz, with that we can't make out, and we need to extract energy from the body through the principle of a resonance. Okay, so these are all about our polymer, that is beta phase PVDF. We used native piezoelectric material, that is PVDF TRFE. We actually, PVDF is a cheaper material. PVDF TRFE is the expensive material. We purchased PVDF TRFE because PVDF, converting this PVDF into piezoelectric material, it requires pooling and all other processes are required. So we procured readily for exhibiting piezoelectric material, that is PVDF TRFE. This is PVDF TRFE. Okay, these are all about this structure. So initially we designed the mask. Our aim was to extract, generate power by using body frequency, and we tried to make 200 micrometer cantilevers, 300 micrometer cantilever. These are the cantilever structures. These structures you can make out, this is the interdigitated pattern. So this pattern we designed by using, see, each dot is a cantilever. Each dot, this is a silicon wafer. Each dot is a cantilever. So each dot, if you enlarge, one dot, if you enlarge, it looks like this. Okay, this is the mask design, and this is the fabrication of the device, silicon wafer, and cleaning process, so and so. And these are the fabrication techniques, fabrication steps. And finally we get a beam or a cantilever. So this is why vibrational energy harvesting system. Okay. So this is about unimorph and biomorph. These are all different comparison of power comparison. Okay. This is piezoelectricity, fly pressure, it generates voltage. And come to our results. This is the design of our cantilever. This design we made by using some software, and this is simulated result. Simulation we have done by using COMSOL multiphysics, and this is the voltage generated. This is here the resonant frequency is around 590, 600 hertz. Our aim was to develop a low frequency energy harvester or vibration sensors. Okay, these are the process fabrication steps for the piezoelectric vibration sensors, and this results. So this is ultimate structure. Ultimate structure, when you observe through FESM, you have got this image, and this is the side view of FESM images of PVD FTRFE micro cantilever with dimension 2000 micrometer per length and 400 micrometer width. And this is the variation midpoint displacement as a function of frequency. Okay. This we checked by using laser Doppler vibrometer. The frequency, that is resonant frequency, we check by using laser Doppler vibrometer. So these results we have published. That is, she is my students, and this is our faculty, Professor Arjun Sunil Rao. He is one of the organizers of this faculty development program. This is myself, and it's my colleague Richard Pinto. He has high experience. His experience, he was around 39 years at Tata Institute of Fundamental Research, and I think yesterday you had a talk. And this is another paper. This we published in high impact journal, that is Sensors and Actuators. And this is another journal we have published, Simulation and Analysis. So I think it's a recent publication, 2021. PVD FTRFE cantilever beams for low frequency applications. So this is for energy harvester, vibration sensors and energy harvesters. And this is the variation of voltage and power output. Okay, so we have got around power. It is voltage is in microvolt and power is in picowatt. Picowatt. This kind of power output can be used in vibration sensors. Voltage and power output values for different resistive loads and midpoint displacements. Okay, this is a fabrication of micro cantilevers and beams. This is beam. The first one is cantilever, and this yellow region is chrome gold pattern. And this is the simulation result, cantilever based vibration sensor, and this is cantilever based vibration sensor. This is actually beam, maybe. Here, no, this is cantilever beam based. This is cantilever based. Okay, 300 micron width. These are the dimensions. These are the dimensions of a beam, and these are the process as I explained. And result shows that the displacement in the resonant frequency. This is for this we fabricated for a different resonant frequency. The dimension is change. You can fix the dimension for a particular resonant frequency. Here the resonant frequency is around 1600. This we fabricated mainly for one particular application. These vibration sensors are used for the health monitoring of bridges, machines, etc. And these results we have published in Smart Materials and Structures, this journal. And these are some of the applications of this one, vibration sensors. And the conclusion is MEMS promises to be an effective technique of producing sensors of high quality at a lower cost. And we can conclude that MEMS can create a proactive computing world. Connected computing nodes automatically acquire and act on real-time data about a physical environment, helping to improve lives, promoting a better understanding of the world, and enabling people to become more productive. Thank you. Thank you, sir.
Thank you. Thank you for and now I also thank all the participants for your kind participation. Thank you one and all. Participants, please note the feedbacks as well as the test links has been shared in the WhatsApp group. Kindly fill all the forms by 6:30 p.m. And tomorrow's session will commence by